compiler engineer on the GNU compiler team working on the ARC processors at Synopsys, and I'm here to talk about our work on simplifying custom instruction integration in GCC for the RISC-V processors. Our agenda for today, we are going to talk about the introduction, who we are as a Synopsys group, the problem definition, and our approach solution. So, as I mentioned before, I'm part of the processor groups at Synopsys. We develop a broad range of processor solutions, from embedded MPUs to high-performance CPUs, covering everything from security-focused cores to DSPs. We also provide neural network accelerators for AI workloads. Our processor portfolio includes an ARC architecture, currently ARC-V2 and ARC-V3, and our most recent ARC-V cores, which are based on the RISC-V. Now let's look at the problem definition. So imagine that we are users, we are customers. We want customization to perform specific operations as efficiently as possible for our workloads. Obviously, we could simply just get a beefy machine and do everything we want to very fast or much faster, but it's such a big thing and it consumes a lot of power, and you can't put it on your pocket. So with that, if we know what we want to improve, we want to tune our processor for it. And when we talk about adding custom functionality to, the first thing that comes to many folks is, why don't we just change the CPU? Well, the truth is, you can't safely edit a CPU. Well, the processor IP that you receive is usually a black box, and there's no support way to patch it. And even if you had access to the Verilog or RTL, it's extremely complex and it's not designed for that purpose. And that leads to our next point. So changing the RTL has major consequences. This CPU development goes into verification. It takes a long time and effort for the development. And it goes to the verification to prove that it works correctly. Now, the moment that you change the RTL, all of those guarantees disappear. And even if the core has safety certified, that certification becomes completely invalid. Finally, even if we could do all of that, we could even add our own extension, but we would need to maintain it and so on, and that creates a mess. We as a customers don't want to deal with it. So instead of patching the CPU, we look for other ways to extend the functionality. So this is where Apex fits in. So Apex stands for ARC Processor Extension, and think it as a plugin system for instructions. So instead of touching the original processor implementation or modifying even the RTL, you simply add new instructions that you need on top of this already there. The best part is you don't need to be a compiler expert to do it. You can simply, we provide, at Synopsys, we provide an approach that takes care of all of that for the integration details for you. That means that you don't have to patch the compiler. You don't have to design or implement or even maintain your own extensions for years to come. You can, Apex makes extending the processor safe, straightforward, and also accessible. Now, there's already existing solutions with Apex. We have Apex support available for our ARC-V processor family on MethaWare, which is our in-house compiler based on LLVM, and also we have for GNU, but not as extended as for the MetaWare. This one only supports at assembly level, although in a compiler we use inline assembly. Now, our focus for the RISC-V course is to align both tool chains to a unified approach. Let's look at this use case. Imagine that we are customers and we call this function which reverts the bits in the 32-bit value multiple times, and we know that these operations are costly, and we want to optimize this. Now, what we do is we call an intrinsic. So we will use the same prototype for the instruction, so that the prototype of the function will basically be the structure of our instruction. And then we will associate that function declaration to an instruction, in this case foo, and then we can simply just do the same thing that we were doing, just call that intrinsic, and then at the end, at the assembly compiler output, he will just take care of everything, register location, etc. It will just print our foo function, foo instruction, sorry. Now, let's try to have a simple overview on how it goes through the whole toolchain. So we start with the C source file, which has exactly what I described. We have a function declaration, we have a pragma that associates everything, and then once it goes to the compiler, well, the compiler will do its magic and eventually emit the instruction. But then comes a problem that the assembler has no knowledge about that instruction. How can he encode to the correct bits and so on? So the compiler needs to do an extra step, which he needs to emit an assembly directive, which all the necessary information is for the encoding. Now, then the assembler, well, gets that information and constructs an internal representation of that instruction. And then once he gets to that instruction, he will correctly map it to the correct bits. But then there's another problem. If we want to disassemble the final ELF file, the disassembler also doesn't have the means to do it. He doesn't have the knowledge about the instruction. So again, we need to create another bridge between the assembler and the disassembler / debugger. And with that, we create custom binary sections at the ELF with the necessary decoding information for that Apex instruction. Now, another step that we need to look for is the linker. So if we have two completion units with the same instruction, everything equals, if it goes to the linker will basically just concatenate all the information, and the final binary section of Apex will be messed up. So we need to take care of that. Then finally, it creates the ELF file. And then, well, the disassembler, which we will talk a little later, will print the Apex instruction. And with this overview, it allows a programmer to add custom instructions without having to modify or even recompile or rebuild the compiler. So how does Apex work? Apex introduces the ability, as we already discussed, about integrating custom instructions, but through a C pragmas and assembler directives. We use intrinsics that look like normal C functions, but they actually are bound to the real instructions. So here, let's look at this currently a normal function prototype, which we call foofunc, and we have three operands: one destination register, and then two potential source registers. Now we want to associate that function to a foo instruction. So we call a pragma intrinsic. We associate the name to the function prototype, then we pass the foo instruction, and then the encoding information that is necessary. And then finally, Apex, or actually the compiler, will finally simply just emit the correct instruction once that intrinsic is called. Now let's try to understand a little more about these Apex directives and how they work. So the function prototype, it defines the intrinsic. And the pragma will specify the mapping to the instruction encoding, bypassing the subopcode, the subopcode, and also the mnemonic. And then we have some properties of the intrinsic. We have some attributes that we can add, and these attributes are listed here. It's XD, XS, I, and C. These we will talk in the next slide, but let's take a focus on the side effect attribute. So this side effect attribute, it will be used so that we will tell the compiler, hey, this instruction is volatile. We don't want you to optimize it. So imagine that you call the same intrinsic like 3 times, and the compiler says, okay, this is pretty straightforward. I can just simply just emit one instruction and then do shifting and so on. It will optimize it. But if we pass the side effect, the compiler will emit the instructions as many times as we call it. For the assembler level, this is, well, the directive that we need to create, or actually the compiler creates. So we pass the mnemonic, the instruction mnemonic, the subopcode that was passed on the pragma, and also all the attributes that are necessary for the assembler to encode the instruction. Exactly. So these attributes are more or less the same. So in terms of XD, XS, XI, XC are the same, but then there's a void, no source 0, no source 1. What's that? So those 3 attributes will tell the assembler if a certain instruction has either not a destination register, or even if it has only 2 operands, or we can even have no operands at all. Just print the instruction, it will do whatever it's defined to. So now let's look at the instruction formats that we have implemented, which are defined mostly the encoding of the instruction. We have XT type, which by default takes 3 operands and it's only registers. Although with the help of that attribute from the assembler, we can have XD with the most flexible operands pattern and no restriction, and so on, etc. So we take advantage for the encoding for the custom 0 field from RISC-V, and then the subopcode that is passed on the pragma is then put across, in this case, from the bit 25 to 31st, and then also in bit 14. And then we have specific places for the registers encoding, and then there's 2 bits that are used to identify that this is an XD instruction encoding. Then we have XS. So the XS type is a little different. It takes an 8-bit immediate operand as a source 1, and but the rest is more or less the same. In terms of encoding, we also use custom 0, etc. So we have a total of normally the 3 operands. For the XI type and the XC, they both take 12 bits immediate, but there's a difference between both of them. So the XI only takes 2 operands by default. So it takes the destination register and then a 12-bit immediate. The XC, on the other hand, takes 3 operands, where the destination register and the source 0 register, or the RS1, are the same register. So it's encoded in the same bit. And most formats can omit the destination register using the void directive, but except for the XC, because this one uses the same encoding for the RS1. Now let's go back to that flow that we had before, and let's look at how the disassembler will take care of disassembling the instruction. But for that, we need to go back to the assembler. So the assembler will emit a section, a binary section called .risc-v.apex, and then more information to it. And that will contain all the metadata to the apex instruction. And the disassembler will just say, take that, reconstruct the internal representation of the instruction, and then eventually print. So for this example of a full instruction with a subcode 13 with XT encoding, the health binary section will look something like this. Another thing is we have a binary section for each instruction, and so that the 1, 11, and 13 there. So the 1 will correspond to the XT instruction format, 11 is for the custom 0 encoding, and 13, well, that would be for the sub-up code. This metadata contains all the information that the disassembler will need to reconstruct the instruction. Now let's take a quick look at the implementation both on the GCC compiler side and Binutils. So for the CC1, our goal is to learn about the pragma and then be able to generate the correct instruction and also the assembly directives. We went through some approaches. So one of them, or the first one, was without no built-in function registration. Then there was two, which was built-in registration after pragma parsing, but without function prototype, and then with function prototype. So for the no built-in function registration, the pragma would be used to record the presence of a special instruction. All calls will be treated, or would be treated as standard calls, but we had its expansion of to emit the custom instruction. So once we'd find the function call, we would have to have a way to intersect that instruction, and instead of being a standard call, it would emit the custom instruction. It's a clean approach, but again, we need to distinguish between the pragma built-ins from the regular prototypes during the RTL expansion. And we need to carry the pragma information throughout the gimbal and 3 SSA up to the RTL expand level. Now let's look into another approach, which is built-in registration with after the pragma parsing, but without the function declaration that we need to do it beforehand. So at RISC-V target files, they called an add built-in function to register a standard built-in. So the thing is, instead of relying, this would create a conflict that we will talk about later on, but basically, instead of relying on the function prototype, extra information would be, from the pragma would be required, for example, the in and out operands, so to know how many operands there will be, and etc. But this deviates from the Apex spec. The function prototype must be present and next to the Apex pragma. And now you may say, oh, why don't you make your life easier, remove the function prototype, put everything on pragma, and that's it. Well, we need to look at this problem from the customer user perspective. It's much preferred to specify the structure of the instruction through the pragma instead of just passing information through the pragma. Sorry, it's much preferred to specify the structure of the instruction through the function prototype that they already have, and instead of creating the pragma, adding more information to the pragma. The other approach is, okay, let's not touch about the function declaration, we will keep that, and let's try to create a built-in. So the add built-in function, internally what it does, it creates also an internal function prototype. So if we already have a function prototype declared by the user, and then we try to add another one, there will be a conflict and there will be an ICE. The compiler will crash. Exactly. So with that information, I try to understand exactly how GCC will differentiate between a normal function call and a built-in. And using GDB, we'll eventually get to a function that will check the function class of the prototype, and you will see if it's built-in or not built-in. And that's using the keyword, the built-in MD. So a standard RISC-V built-in would have the function class set to built-in MD, and a normal function call will be set to not built-in. So our solution is pretty straightforward. We just need to mark the existing function prototype as built-in MD. And that way, the compiler will just, once he gets to that function call, he will see, okay, this is a built-in. Let's send it to the backend files for the expansion, to the target specific files for the expansion. So exactly, the result is the call remains normal, but during expansion, it's treated as a built-in. So let's look at the flow of the compiler real quick. So after the pragma parse, we need to look up all the function declarations to try to match the one that we are looking for. If we don't find it, then, well, we will print out a warning and ignore it because we need to find that function declaration. That's according to the spec. We will mark the function declaration as a built-in so that the CC1 will treat it as specially. Then we will store the reference to the Apex metadata in the function code of the function declaration, which we will use for a little bit later. We now, based on the operands of the function declaration, we will assign an instruction code which will map directly to our machine description pattern. This one is a simplified one, otherwise it will take way too much space. In this case, like example, we have a function prototype with 3 operands. It will map to this one. And then let me talk about that later. So it will map the instruction code, which is this name right here after define instruction, to that Apex instruction. And finally, we will store the Apex metadata well in the buffer and so on. So once the compiler encounters the intrinsic call, he will expand to the target-specific files, which eventually will extract the function code. We will look up the instruction information, and then we will pass the necessary information to the machine description. Now, there's one thing that we needed to do is the mnemonics. In GCC, the instruction mnemonics they are defined, hard-coded already in the machine description files, but in our case, it's not. I mean, we don't know what's the instruction mnemonic until the user decides to specify it. So we had to be a little creative in this. So during the expand, well, GCC will allocate the correct operands based on the function declaration and so on. And there we will inject another operand. And that operand will be the reference to the Apex instruction. So in this case, you see this, the ID 1, which is a constant operand. This one will actually be the reference to the Apex instruction. So this code is simplified, it's a pseudocode, but basically what we do, we just extract the E index, which is the reference from the operand 1. We go into the buffer that has the information about the Apex instructions, go to the index, and then we extract the instruction name, the mnemonic, and then we can simply just reconstruct the instruction, the final instruction with a mnemonic, and great, that's it, it works. Now, for the disassembler, for the Binutils implementation was a little more straightforward. We just needed to read the directive from the assembly, the compiler output assembly file, and then build an internal instruction representation. This instruction representation, then it will be mapped to the correct encoding, and we will also write the Apex metadata in the binary section that will be used for the disassembler. And the disassembler the implementation for the disassembler is basically just doing the reverse. You will parse the information from the binary section and then reconstruct, again, from the same logic, the internal instruction representation. And then once the encoding is found, it will print the correct instruction. For the debugger for GDB, luckily there was no need to change anything. It just worked out of the box with all the mechanism from the disassembler. Now let's look at our conclusion. So what Apex does not cover? We don't cover floating point registers, and also, well, currently also not vector registers. And there's one important thing, which is the latency and resource usage. So we don't, for now at least, we are not taking into account the scheduler. So luckily, this works for interlocked CPUs, where the CPU will stall in case he needs information that is still being executed in the pipeline. Otherwise, this would be an issue. And yeah, we restrict ourselves for the operands and encoding, and by this means we are quite restrictive about the backend optimization. Now, a real quick demonstration on how it works. So we have defined here an apex instruction, which is called apex xc sub, which the idea of this instruction is just to subtract one value from the other and then put the result to the destination. Pretty straightforward. So we just call that function, we pass 8 and 2, and we expect to have a return value of 6. Now, we can also look at the disassembler. We will disassemble main, and you can see that the disassembler managed to map the correct mnemonic and also the registers to print to the user, which is great. Now, if you want to debug or even try this out, we need a simulator with support for Apex. Luckily, we do have an NSIM simulator which has extended support, so we are able to debug our functionality, which is exactly what we did here. We start NSIM stub, and then we connect with GDB to the simulator, and then we can step over the instruction. We can print the register value, in this case is x0, and you can see that the correct value is was returned to the register. So conclusion, Apex is a method or an approach to integrate custom instructions into the GCC Binutils toolchain. Allows fast ISA prototyping with using a custom simulator which provides support for Apex. It does not consider resource usage or the scheduler and so on. It's limited in that aspect. The approach is beneficial for interlocked processors. We have plans for upstreaming this approach, not necessarily how it was implemented, but the idea of Apex to the upstream. In this case, we are only targeting RISC-V backend or RISC-V target files. We don't touch anything that is generally for GCC compiler, and the same for Binutils. So if you want to find our approach and how everything worked out and how it was done, I believe here 2 links with points to the pull requests created both on the compiler and Binutils. It's easier because you will find all the commits or most of the commits there. There are some fixes that we had to do later on in our main branch, but you will get the whole idea there. Thank you, everyone. That is it.
So just a couple of notes on the limitations. It doesn't look like you have the support to handle relocations. So you can't, for example, create an extended branch kind of instruction with this framework.
No, we don't take that into account.
Fair enough, easy enough. Yeah. Along the same lines, in the registration of your built-ins, for the RISC-V port, registration of a scalar built-in is significantly different than registration of a vector built-in. So you're going to have to do some work there. This gentleman might be able to help you. Maybe, Keto. But it is dramatically different. So it's just 2 things to be aware of as you look towards the upstreaming process.
One question for you, Jeff, by the way. Do you think the hack of changing the function declaration to have a built-in too invasive, or?
Don't know until I see the actual code. I'll reserve comment until I see the code.
The code itself is pretty straightforward, but yeah, sure.
Yeah.
Curious about the implementation side. Why you decide to use in the pragma rather than the function attribute? Since what my inspection is, using the function attribute should be much more easy to handle that on the LTO, since LTO will have some issue for the built-in ND ID or something like that.
I'm sorry, I didn't follow.
Let me split the data into 2 questions.
Okay.
Do you have tried to implement that with a function attribute rather than the pragma?
I believe not.
Okay. And the second is I in my experiences, pragma is kind of maybe more complicated to handle that during the LTO. But I guess your solution is just change the jumper or tree declaration, so this should be gone.
Now,
I think there's a question. How does this interact with LTO in general?
Yeah.
That is really the big question. I'm concerned, but I don't have a specific concern.
So I guess maybe to explain a little bit, there is no expectation that it will be instruction which simplifies those jumps or something like that. So that's for very specific things to think about, like CRC calculation if you are doing storage or something. And in that case, what Luis has mentioned, merging of these things is dangerous because typically if you want to do something with your real hardware, you don't want to merge two operations in one because it was meant to do 3 different operations. And in that sense, in LTO, it will be treated just 3 separate operations, and no optimizations are meant to be done around that. You just keep it because...
About the optimization of the LTO space. I'm just struggling. So I'm not concerned about the optimization aspect, but LTO and its interaction with built-ins has been a, how should we put it, Keto, a sore point, a problem area. I don't know what term to use, but there's this a bit of uncomfortableness around the LTO question because I'm not sure it's been explored. That doesn't mean there's necessarily something wrong. It's just I think it needs to be explored. Does that make sense?
Yeah, but
Okay.
in fact, LTO is quite widely used by our customers.
For good reasons, because they want to be as efficient as possible. And yeah, we'll try to explore if it blows up something or not. Because I understood that you expect that it might be some functional problems.
It's been a worrisome area. He's going to run.
Yeah, I was talking to the cat.
Kind of one random thing come to my mind is maybe we could consider to just expand that into inline assembly statement in very early stages, so that this should prevent a lot of problem, either in the tree level or the RTO level. But just a quick idea from my mind.
Does anybody else want to ask a question?
Another,
So one of the reasons for the talk was actually to kickstart discussion of approach like that. So if you guys have any, so first review comments are more than welcome, and patches will be sent out very soon. But if there might be something before even, so that we don't waste cycles on the mailing list and may have discussion in that audience or after, it would be definitely nice, because hopefully there is a nice and elegant way to do that. Though it is not like super universal, as you see, that requires hardware support. This is not going to work for any existing SoC, but how to do that nicely, because our intention is to have it fully in upstream and not have any downstream modification for that at all, if it makes sense.
Yeah.
But you will tell.
And I think your example of CRC is a great one. If you think about the CRC question, we have careless multiplies with the BC extension, but you can do better. If you can embed a polynomial and you can have a true CRC, and this is a way you can expose it. So I think there's value here. The question is just going to be nailing down the implementation details.
Another point that I want to point out is that we map. So that I forgot to mention during the presentation is that in relation to the instruction formats which define the encoding, we can omit that from the pragma, and then GCC will, or CC1 will decide which one to use based on the operands from the function prototype, and also the sub code value limit to fit inside the encoding. And from there, then in the emission of the instruction, the compiler will decide which one to use if it's available, if he decided to enable it, and also for the constraints. Because imagine that, okay, we have XS and XD enabled. XS takes an immediate, but a maximum value of 12 bits. But imagine that it takes more bits. He will, instead of using XS, he will use XD, which takes registers and so on. So he has their dynamic. The machine description pen that I put there was really simplified with only one alternative, but we have multiple with 2 up to 3 alternatives so that the compiler can decide.
Yeah, it makes perfect sense. If you use the alternative constraint mechanism, you can support the various formats easy. Yeah.
Okay, that's it. Thank you, everyone.